That I don't know. That'd be crazy. Mhm. I'm wondering if your floaters are gonna be.
I didn't see this.
Okay.
Yeah, no. Career, maybe.
Okay. It's also trying to base. Yeah. Yeah.
A lot of people out there.
It's going to be hot.
You do ask.
Yeah. If it's already one baseball too. Yeah. I know. I don't know. I don't want to. One thing I can carry it, I can make it work. What else? History. Well, yeah, I can drop it. Yeah. You guys should. Yeah. Yeah. That'd be good. I want to keep the water too. Ask me about like trying to the baseline. I just said with the butter. For me, I was doing that. Figure this out. I hate you.
I'm always like, I was. My pressure.
Here's the thing.
Hi guys, if you can turn to page 16.
Well, why two? It's not.
Pretty sure. This close.
Okay, page 16.
For some reason.
Let's go to 42. And then we're just going to kind of work through the bottom half of the page here. We're just finding derivatives. These are the rules that we've worked on so far. Log derivatives, natural log is u prime over u. And then exponential function e to the u is e to the u times u prime. We're going to be building off of these to extend it to derivatives of other bases. But we're going to kind of get some more practice with these two now. I have it on the board as well. And let's look at 42. Okay, page 16. All right, so 42, we see the need for exponential function e to the u. But look at how the expression is set up here. What do we have to involve as well? Now rule and product rule. Yep, x squared and e to the x, they are multiplied. So we have to go through product rule. We can't just take the derivative of x squared and e to the negative x and just leave it at that. We got to go through product rule because of the way that they're interacting with each other through multiplication. Okay, so let's set up using product rule. I'm not going to be picky about how much you clean up. The important thing is you can get to the derivative and just clean up slightly. That should be good enough. There's no need to find common denominators. Okay, so f prime g plus f g prime. Okay, so x squared becomes 2x. G is just e to the negative x. Back to f, that's just x squared. Now, what's the derivative of e to the negative x? Good. So all we're doing is we're just following what the rule says. So we identify our u value as negative x. So the rule is simply e to the negative x times the derivative of the exponent, which is negative 1. Yeah. Okay, from there, the hard part is done. We're just going to do a little bit of rearranging. I'm not going to, I guess I could have gone even further and found common denominator. I just put the two terms together. I moved the negative 1 in front, subtract the two expressions, and there's my derivative. Take a look at 43. Also, we're just finding the derivative of all these expressions here. E to the negative t plus e to the t quantity cubed. Obviously, we have to involve exponential function e to the u, but what else? Same rule, yep. Outside, inside portion. Yep, outside's derivative times inside's derivative. Okay, we take turns with each portion's derivative. Parentheses cubed, we can go through power rule, and then the inside e to the negative t plus e to the t. We can handle them individually with the e to the u rule. So first things first, my outside's derivative is 3 parentheses squared. Keep the inside intact. And now we can look at each individual derivative. So e to the negative t becomes e to the negative t times negative 1. Okay, so there's negative 1 that's going to be left over from that u prime. What's the derivative of e to the t? Yeah, just e to the t times 1, and really that 1 is not going to make any difference. So this is an instance where you see the derivative it's the function itself. Okay, so that's a unique feature about the exponential function, is that the derivative and the function are identical. We can do a little bit of cleanup, not too much. I'm just going to move that negative 1 in front to make it a little cleaner, but okay. All right, 44. So 44 looks like we can jump directly into our rule for e to the u times u prime. But if there's something that we can do so that maybe our u prime can be a little bit easier for us to work through. Well, let me ask you this. How would you go about finding the derivative of negative 3 over t squared? Yes, quotient rule is fine, but is there something a little cleaner, a little easier, a little faster? Yeah, if I bring the t squared to the top, I can avoid quotient rule, and I can just do a little bit of a power rule, right? So I'm always looking to avoid quotient rule, especially if my numerator is a constant or if my denominator is just a constant. Those are, we'll see some problems like these where we can quickly avoid quotient rule if possible. So I'm going to just rewrite it. Make it e to the negative 3 t to the negative 2. So now that exponent is ready for my u prime. So my derivative is e to the u times u prime. That's a lot easier to do rather than having to go through quotient rule, right? 6t to the negative 3. Okay, so that's my derivative. I can kind of do some rearranging to get my negative exponents to clean up visually. So it's all, I can put everything under one fraction. The 6 will stay up top. The e exponential function e will go to the denominator. Oh, sorry. I guess we could, but we can leave it at the top as well. Again, I'm not going to be too picky about how you clean up your expression. If you can find your derivative, that's really my main goal. All right, 45. Okay, 45, natural log of 1 plus e to the 2x. I want to keep reminding us that, yes, if you see a natural log expression, you always want to consider the possibility of expanding, right? And we have a couple of expansion properties, but this is not one of them. Okay, if it was natural log of a times b, I can expand it to natural log of a plus natural log of b. But if it's natural log of a plus b, I can't distribute the natural log through, okay? Because natural log is not outside the parentheses. That parentheses is inside the natural log expression. I can't distribute something that's inside the expression. So I know visually it makes sense, but it doesn't make sense for this problem. So we're kind of stuck with that u value. We have to go with it. We have to jump directly into u prime over u. All right. So what's our u prime? What's our derivative for that parentheses expression? E, yeah, 2e to 2x, or you can say e to the 2x times 2, and the 1 just disappears. So u prime over u, right? So it's e to the 2x times 2 divided by the original parentheses there. Okay, take a look at 46. Okay, take a look at how 46 is set up. Is there anything we can do before we jump into our derivative process? Quotient property, right? Yep. So I have natural log of a over b. That is a messy parentheses. Thankfully, we have something to split into, allowing us to split that fraction into two separate expressions. So natural log of a over b can be expanded into natural log of a minus natural log of b. So now that we have two individual terms, our u value is a lot easier to work with, and then we can just do u prime over u twice for both terms. So try that, see if you can work your way down to the derivative. And we're going to have to involve both natural log and exponential function derivative. U prime over u for both expressions. And that's fine. No need to find common denominator. Okay, next page. Let's try 47 through 49. Right, and then we'll look at today's topic. So look at 47. Next page. Okay, 47, I have 2 over e to the x plus e to the negative x. How would you approach this problem to find the derivative? Quotient rule is possible, but we can bring it up, right? You see that numerator is just a constant. The nice thing about a constant is whatever you bring up next to it, it just becomes part of it, right? It doesn't have to be its own thing. It can kind of just be a part of whatever variable that you bring next to it. So if I bring the denominator to the top, I'll have to make it parentheses, bring it to the what? -1, yeah, which means I gotta go through chain rule, right? So I think we prefer chain rule over quotient rule. It's not wrong if you decided to do quotient rule, but it just feels a little bit cleaner going through quotient rule. Sorry, going through chain rule. So chain rule, we identify the outside, which is that 2 parentheses to the -1. We identify the inside, which is e to the x plus e to the negative x. And then we just take turns with each derivative, right? Outside's derivative with power rule, inside's derivative with exponential e to the u rule. So outside's derivative is -2 parentheses to the -2, right? Bring down the exponent, subtract 1 from the exponent. Keep the inside expression intact. And then we take turns, and then we take the derivative of the inside portion. There's 2 terms, so we take the derivative of each. E to the x is just e to the x times 1. E to the negative x is e to the negative x times -1. Do what we can with cleanup. Any questions so far? Okay, take a look at 48. E to the x minus e to the negative x all over 2. How would you approach setting this up for its derivative? You see denominator, but we can avoid, and we should avoid quotient rule. And how can we do that? Yeah, let's just either split up into individual fractions or exactly right. Put a 1/2 in front and then distribute the 1/2 through. And now all of a sudden you just have 2 individual expressions that are relatively easy, right? That 2 is looks complicated, but once that 2 comes out, right? If I split up into individual fractions and then understand that the 2 is just the same thing as saying it's 1/2 times e to the x or 1/2 times e to the negative x. Once I get that 1/2 to show up, it just feels a lot easier, right? Visually, I mean, it's the same problem, but visually we're just have an easier time looking at a number in front rather than looking at a number under our variable. Okay, so we just apply the rule for e to the u times u prime for both these terms, and the 1/2 just hangs out in front. Okay, take a look at 49. Okay, look at how 49 is set up. Why don't you do this one? yeah, this one, we really can't avoid quotient rule, right? I got two expressions. It's not a natural log expression. I can't expand. I guess technically we could do natural log of both sides, but it's probably more trouble than it's worth. Let's just go directly into quotient rule. And then we'll find our derivative. Okay, so f prime g minus f g prime all over g squared. Okay, take the time to expand a numerator. I know this looks tempting, right? To try to just take these out, but that minus is preventing us from doing that. So we just got to distribute through, combine like terms, and see if we can get our numerator to clean up a little bit more. What happens when I do e to the x times e to the x? What I do to the exponents? Good, right? It's not x squared, right? We add the exponents. So e to the x times e to the x is e to the 2x. Okay, so after we combine all those terms, get rid of the parentheses, combine, we just get negative e to the 2x over e to the x minus 1 squared. Okay, so let's move to today's topic, which is on page 19. Derivative of logs of other bases and derivatives of exponential functions of other bases. Okay, I'm going to skip some of these examples here, and instead, I just want to talk about how we can kind of move towards the rule that we're about to use. So if you can just use the space that up here, you can cross out example 1 and just copy this down here. So we know what. Sorry. We know what log derivative natural log is. Natural log of u is u prime over u, right? And as a reminder, that natural log is a shorthand way of saying log base e. Okay, it's the same thing, but a lot of times we don't see it this way because it's just easier to write it as natural log. But understand that natural log is log base e. Okay, exponential base e. And that's why natural log and e to the x are inverses of each other, because these are both base e. Okay. So we could say log base e of u equals u prime over u. It's the same thing. Okay. Now, what if we wanted to find the derivative of logs of other bases, right? What if it wasn't base e? What if it was base 2 or base 3 or base 5 or base 10? They all kind of follow a different set of rules, but very similar to this. We can think of this as the parent function, and then all the other bases is just going to be adapted from this simpler expression. Okay. So here's what the rule looks like. If I have logs of other bases, I'm still going to get that u prime over u, but there's going to be a little bit of conversion that needs to happen because it's not base e. So basically, if it's other bases, we're basically converting into base e, and then we're doing u prime over u. Okay. So if we think about it that way, then it feels like we're just tacking on an additional something to our derivative rule. So let's say, so now the rule that we're going to learn, that we're going to work out today is log base a. Okay, so log base a, that a can represent bases of that's other than e. So base 2, base 3, base 5, base 10, base 15, they all fall under this category. So if you compare between log base a and natural log, they are virtually the same,
right? You still have that u prime over u, but there's an adjustment that needs to be made. And that adjustment is 1 over natural log of a. So just think of that 1 over natural log of a as just some coefficient that has to sit in front of the derivative because it's not base e. So if it's log base 2, then I gotta do 1 over natural log of 2. If it's log base 7, then it's 1 over natural log of 7, and then I do u prime over u. Right. So we're gonna practice with that rule. And yeah, sorry about this here. I made a mistake when I made this key or made this worksheet. It's not u prime over u prime, it's u prime over u. And also I like to have that 1 over natural log of a in front rather than underneath my expression. And that just feels a little bit cleaner. I don't have to, and also I just think of it as it's just some coefficient that has to be in front of my derivative. So I'll rather write it this way. So some numeric coefficient in front of my derivative. Okay, so let's try this problem here and see if we can make sense of this derivative rule. Oh, and then something else to keep in mind is that all of the natural log expansion properties also applies for logs of other bases. So if I see an expansion property that's available for log base 4 or log base 6, I can take advantage of it. In this case, I'm not going to be able to, there's no expansion, right? Because that minus is preventing us from doing anything. Now, if it was x squared times e to the 2x, then we can expand. So yeah, all the log properties still stands, doesn't matter what the base is. Okay, so we're kind of stuck with this u value. We're just going to have to jump directly into our derivative rule. All right, what's our a value? 4, right? So you can jump into our derivative rule here. So f prime equals 1 over natural log of 4. Okay. Okay, so the reason why it's natural log is because we are basically converting into base e. And that way, once that's converted, then it just becomes the same u prime over u. Okay, but it's just a number. Okay, it's not a variable, it's just a number that has to hang out in front of my derivative. And now the rest of my derivative feels the same as natural log of u prime over u. Okay, so u prime, we gotta take each derivative separately. X squared becomes, okay, and e to the 2x becomes, good. Yeah, I can put that 2 in front, or we can put it after and then adjust it later. E to the 2x times 2, or we can make it 2e to the 2x, okay? But don't forget, all divided by what? U value. And your derivative is just going to look a little messy, but I'm not going to ask you to clean up much. Okay, you can you know, pretty much leave your answer in that form, and I'm okay with that. Okay, or if you want to try to get it all into one fraction, that's fine as well. Okay, not going to be picky about how you present your derivative. It's just all, you know, with logs of other bases, it's just going to feel a little messier. Okay, let's do some more practice with example 3 here. This is log base 5, so we know it's going to be log base a, right? Again, I don't want you to think of this as a brand new rule. I want you to think of it as an extension of natural log, right? Still a log, you still u prime over u, just a little bit extra to adjust for the fact that we're not dealing with base e. Okay, is there anything that we can do to maybe rewrite the problem to make it a little easier to work with? Yeah, rewrite it as what? Raised to the 1/3. All right, anything else we can do before our derivative process? Yep, that's right. This is not power rule. This is not derivative. This is just expansion. So natural log, we can do it with that 1/3 in front. Same with other bases. That exponent can come down. So anytime I have a log expression or natural log expression, I'm always trying to taking advantage of my properties so that my derivative will be a little bit easier. Okay, so can I now jump into my derivative rule? Okay. Wow, there's a couple things we gotta keep track of, okay? There's that 1/3. That 1/3 is gonna hang out in front. There's that 1/ln of a. That's another coefficient that's gonna hang out in front. And then we can do u prime over u. So it's gonna feel like there's a lot going on because we have all these things that's gonna sit in front of our u prime over u. Okay, so that 1/3 is just gonna hang out in front. Times, okay, what's next? Yeah, 1/natural log of 5. Another coefficient that has to hang out in front. And now it'll feel like my natural log rule, u prime over u. Okay, what's u prime? 4x and 2x squared plus 7. Okay, this is fine if you leave it like that, but if you want to merge together, you can, or at least put it under one fraction. Okay, what do you notice about number 4 that that we should consider?
There's no log base.
Yeah. There's no base that's visible to us. But there's a base there. You know what that base is? Base 10. Yeah, because we have a shorthand way of writing base e, because base e and base 10 happen so much. We have an abbreviation for them. So log base e is natural log, and log base 10 is just log. Okay. But we can put that 10 there just so that we can kind of see, because we're going to have to eventually keep track of our base. So, okay, so log base 10. I'll put a 10 there. Okay. What else can we do maybe before we do our derivative step? Yeah, we can use expansion property, right? Because if I have natural log of a over b, I can also do the same thing with log of a over b. Expand into log of a minus log of b. I'm going to put the base there just to so we can see it clearly. All right, anything else we should do before our derivative? And which exponent? The 3. Second one, yeah. Second one, this is a good one to move. I mean, if you want to move this cube here, you have to separate the 5 and x cubed first, and then the 3 can come down. It's not worth the effort because that 5x cubed is already pretty easy to work with. But this one is worth moving because otherwise you got to go through chain rule. So the first one, we can't move that 3 without expanding. But the second one, let's go ahead and move that one. Okay, we're ready to apply our new rule here. Y prime equals. Okay. Just like natural log, just with a little bit of extra in front over, yeah, natural log of 10. So you can do that, or you can push that coefficient in front and deal with it later. Okay, I can clean that up later, or if you already cleaned that up, that's fine. Okay, a couple of things got to keep track of. There's the 3 that's going to have to live there. The 1 over natural log of 10. And the u prime over u. Okay, we do some cleanup here. Get everything under one fraction. I can reduce the x squared and x cubed. I can reduce the 15 and the 5. Fifteen and 5 reduced to be 3. X squared and x cubed leaves me with just an x in the denominator. The second fraction, I'm just putting it on the numerator, assigning the numerator and denominator parts. You can, yeah, or I can leave it the way it is. It's, yeah, I'm not going to be picky. Okay. Page 20. Okay, so let me go back to this. Okay, these rules that I have here. So we talked about how natural log base e, we can create derivative rules of logs of other bases. We just have a little bit of adjustment needed in front of our u prime over u. Okay. A similar process is going to be applied here. If I have e to the u, I know my e to the u is e to the u times u prime, right? So let me say it this way. E to the u's derivative is the function itself times the exponent's derivative, right? Function itself times the exponent's derivative. So e to the u is an exponential function. But what if we have exponential functions that's not base e, right? What if it's 2 to the x or 3 to the x or 5 to the x? And we have a similar rule that we can apply. But again, there's going to be some adjustment. And that adjustment is also going to be involving natural log of my base, natural log of a. So if you look, this is the rule for a to the u. So a represents base 2 or base 3 or base 5. We can all categorize it all under the umbrella and call it a to the u. So if I have a to the u here, I want to show you the similarity between this and e to the u. So first we got to make the adjustment. So natural log of a basically does the job of converting it into something that feels that is manageable. And then look what we have. The original function times the exponent's derivative. Same thing here. Original function times exponent's derivative. So if we feel comfortable with these two derivatives, then even though this looks messy, you're just thinking of it as that you're just adding a little bit extra and adjusting it to adapt to other bases, right? But the structure is the same, right? You're kind of building off of the same rule. Let me just, okay, so the quiz, which is next Wednesday, we're gonna have to memorize these rules. I think the biggest issue that students I think experience is not or just forgetting where that natural log of a goes. It's like, is natural log of a in the numerator or is it in the denominator? So what helps me remember is I look at my derivative, right? U prime over u versus a to the u times u prime. If I see a denominator, that helps me remember, oh, my natural log of a goes in the denominator. So because I know that u prime over u is natural log, anything with log has a denominator derivative, and that helps me remember there's a natural log of a. E to the u times u prime, a to the u times u prime. There's no denominator, so that helps me remember that natural log of a is going to be in the numerator. And also know that I know one is going to be numerator, one is in the denominator. So that u prime over u kind of helps me remember where that natural log of a goes. Okay, so let's try example 5. Okay, we have 5 to the x squared minus 2x. This falls nicely into an exponential function, base A raised to the U. So what's first? Natural log of 5. So that's just some number that's going to have to hang out in front times the original function, no changes, multiplied by exponent's derivative, 2x minus 2. All right, careful that you're not trying to merge any of these together. This is stuck in this form. This 5 is not free to move. We can't make this natural log of 25, okay? So all this is kind of separate. All right, example 6. Again, we see an exponential function for a to the u, but there's an x in front, so to involve that, what else is needed if we want to find the derivative? Go through what? Product rule. Yeah, we got to go through product rule. So f prime g plus f g prime. Okay, so f prime, x becomes 1. We keep the g function back to f, which is x, and the derivative for 4 to the negative x is natural log of a times the original function times the exponent's derivative. Not much we can do to clean up. So this is fine. Yeah. Okay, any questions? So tomorrow we're going to try to put things together, just do some review with these rules here. So tomorrow, if you can look at page 23. Okay. So tomorrow you'll be working through page 23. 24 is the key. So we'll practice through this. And also I'm going to give you some time in class to try to do some catch up with your homework. And I will check 5.5 homework on Monday. Okay. I'll check 5.5 homework on Monday. So tomorrow, give you guys a chance to do this. Do some catch up work. Okay.
Getting very late.
So, okay.
Yeah.
Hi.
All studying on choice. I don't. I usually do software was fun. I usually do that. I don't do help. The only class that I can enjoy is like show.
Yeah. What property of E like makes it so perfect for all this function?
Yeah, let me see if I can give you an answer for that. The nice thing about it is that it just works so seamlessly with derivative. So yeah, I don't have a really detailed answer for you, but basically I can work on that and get it to you.
I figured, I mean, I know it's not there, but I feel like some things online. Oh, its derivative is always equal to its function or something along those lines. And maybe that's like,
Yeah, it's just so interesting because e to the x looks like right? And it's so interesting. Every order pair also gives you the slope value. So here, this is y is equal to e to the x, right? And then y prime is equal to e to the second. So basically, this derivative and the order pair lines up. Right? It's e to the 0, the order pair e to the 0 of 1 but then the derivative of e to the 0. So this point is telling you the order pair and the all these that we're telling you. It's such a fascinating thing, but yeah, let me see if I can give you a better answer.
I'm sure there's a very lengthy.
Also, I think that.
Next two questions.
Yeah. It's good.
I'm just saying.
She said she was gonna do it.